Thank you. We're now supposed to have half an hour of discussion, but I think we overran a bit. That is now down to 10 minutes. However, I am going to open the floor for discussions. If anyone wants to start off with a question, this is your chance.
Yeah, I will open. I commented on it on Slack. Albert, you raised 4 questions at the end. Maybe you can put them again. And as I commented, your first question was, are the shaping mechanisms of massive and low mass stars the same? And I think yes, and I think this is also connected to the talks on AGB stars. Several of the processes that are taking place in AGB stars, single and binary, also take place in massive stars. And so I think if we take the answer to the question, are the shaping of nebulae of massive stars and low mass stars the same? If we take the answer to be yes, we can learn a lot from massive stars about planetary nebulae and the opposite. And so I think I have, your 4 questions, I have answered to 1, yes. The shaping is the same basically. Sometimes they are different. If you have a neutron star companion or a black hole in massive star, you have some new processes there, like neutrino cooling. But the jets do their operation, and we have the inner ring of supernova 87A is very similar to the one of the necklace. So I'll stop here.
Yes, I have to, well, I agree with you that you see the same structures and that the mechanisms that go in low mass stars will also act in high mass stars. But there is one difference. The high mass stars still have rotation, and the low mass stars lose that. If you have more than 1 billion years of stellar evolution, the star no longer rotates.
No, if the progenitor of 87A
has all its rotation.
Progenitor of 87A or Eta Carina expanded by a factor of 5 or 10. By that time, if there is no companion, the rotation is very low. So I talk about evolved stars. When I take evolved stars, even massive star evolve, even Eta Carina, because of Humphrey-Davidson line, doesn't become really cool, still expand by a factor of 5. So my view is that, you know, the basic processes are really the same. And, you know, I compared, there's a paper of that rectangle and Eta Carina and others, all the times I compare with them, and the more I looked at them, they become more similar, even supernova remnants.
Good, can I throw another question into the group? We've heard about companions to AGB stars. We've heard that 30% of AGB stars are asymmetric from the CO surveys. We found that a lot of AGB stars in the UV and X-ray show indications for what may be companions. Main sequence, I think, in most cases, although the flickering might work better with white dwarf companions. Are these the companions that we are looking for, or is there more to AGB companions than this UV access?
What do you mean the ones we're looking for? You mean the ones that affect the shaping?
That the ones that can explain the kind of structures that we see.
Well, I would volunteer to say that the good thing about the ultraviolet is that it's actually showing that there's active accretion going on. And I think most people would agree that you require accretion to make accretion disk and to produce jets. So in that sense, I think the ultraviolet is actually really probing the scene of the action and the companion, which is actually responsible for producing the asymmetries.
Is this Roche-Lobe accretion?
Well, it could be different things, right? I mean,
because Roche-Lobe accretion, it would be extremely unstable. It would relatively quickly lead to common envelope.
Yeah, so obviously these systems are not in the common envelope phase. Of course, they may enter into the common envelope phase. I don't know.
Can I just interject? Raghvendra, that was a really interesting talk. I agree, and I think understanding the nature of these companions is maybe the next step, right? Did you you showed in one case that you thought you were seeing X-rays from a main sequence companion's corona, but I put the comment into the chat that 10 to the 30 ergs per second is enormous for a late type main sequence star. The sun is down at whatever 10 to the 27 or something like that. So it requires something else going on at the companion, which is interesting in itself. It sounds like the companion has secreted angular momentum and been spun up and rejuvenated. What about the other companions that you're seeing? Can you say anything about them yet?
Well, I mean, this is one object where the accretion powered emission is low for whatever reason, and therefore we think that we are seeing the companion because the temperature is relatively low. But if we get more such systems where we think that we are seeing, where the emission is consistent with it coming from the companion rather than from the accretion activity onto the companion, then we would be able to say a little bit more. But you're right. I mean, the corona, the emission is the luminosity is very large, and some kind of supercharged corona or something. It's hard to tell. Maybe there is a contribution of accretion as well. It's very difficult to tell, of course.
Yeah, you can often tease out whether you're seeing accretion in the X-ray. Well, often there are like a half dozen cases, maybe 10 cases among young stars where you can see the signature of accretion in a soft X-ray excess that you don't expect from a corona, and from dense plasma that you can measure if you're lucky enough to have enough signal that you can look at line emission in X-rays. But that's very tough, and it's going to be impossible, I think, until we get the next generation of X-ray X-ray observatories. But yeah, I think it seems like you're onto something interesting, and following up on these companions in some way, shape, or form is really important.
One thing I was thinking about, and I would like if you guys have any interesting thoughts to offer, is so. As I said, if it's chromospheric emission, we can't tell, of course, whether it's the chromospheres around the companion or the chromospheres around the primary. So I was wondering, we should think about observational diagnostics to tell the difference. Maybe, some ultraviolet study or X-ray study. So that would be something to think about, because if we can show that the chromospheric, even if it's chromospheric emission is from the companion, then that would say that the vast majority of UV emitting AGB stars, all have companions, which would be quite interesting.
The frequency spectrum may help. If it's a compact source, then you get a turnover in the frequency spectrum of the flickering. We never had enough data to see that, but it was in principle a way to separate white dwarfs from main sequence star components. Therefore, it should also separate the main sequence companions from the AGB star.
Make a note of that.
Is there any way you can tell the mass of your companion if it's indeed it is a companion with any within points? Is it a 0.5 solar mass main sequence star, or is it a 1 solar mass main sequence star?
Well, so in the case of Y Geminorum, where we have the most data, we estimated the mass of the companion based on assuming that the outflow speed is comparable to the escape speed from the companion. And so then it comes out to be about half a solar mass. I don't remember the exact number, but yeah.
Because it's just really hard to do mass transfer between an AGB star and a half solar mass star and keep it stable enough to see 30% of AGB stars in that condition. They tend to be very unstable and lead eventually to common envelope or merger. Unless they're more massive, in which case you have a greater degree of stability, and then you might have a different type of interaction that lasts longer.
Yeah, but I mean, what is this time of instability? That is, we may be seeing all these systems before some of them will go into common envelope.
That's right, but if you imagine that time of mass transfer when you're detecting them to be a very unstable phase, lasting very short, you don't expect 30% of your sample of your population to be in that extremely short-lived phase.
Can you put a number on the time?
Wind slope overflow?
Well, that would be different. That would be a different amount of accretion, though. Would you be able to distinguish between them?
No, we have
That-
examples, Maya. What do we see?
Alright.
Well, we made a very interesting point. So maybe that is telling us that the fact that we are seeing, if we can show that these are companions in all the UV emitting stars, then that is telling us what configuration there is and what kind of accretion is going on.
Can I raise another point? That is, we've talked about common envelope, and we see the post-common envelope systems for certain. But what would we be looking for on the AGB? How can we distinguish the kind of objects that become the post-common envelope systems that we see? Is there a way to recognize them from CO observations, UV observations? The discussion is quite dominated by the people who will speak most easily. And I realize that. If others want to inject but don't feel quite free, just raise your hand. Yeah. Otherwise, Ursula, your chance.
May I invite the younger people who often don't feel like talking, and particularly now on Zoom, it's a little bit threatening. Why don't you just post on Slack? Just put your thoughts there.
And then maybe we could read them, like some of the senior people could read them just to make sure that the junior people have a voice.
Yeah, so the conversation can also continue on Slack.
Yep. But I'm still waiting for an answer for the question.
Yeah, I think what we are looking for is what we are looking for. We are looking for non-spherical shape. So if you look at an AGB star and you see non-spherical, really non-spherical, bipolar, whatever, disk, name it, and you claim it's a single star, it's not a single star, it's a merger product or the companion is below detection limit. So what we are looking for is what we are looking for. We are looking for asymmetrical post-main sequence system. And when we find one, AGB, post-AGB planetary nebula, we found a binary. This is my claim, because I don't see how an evolved single star can make a non-spherical nebula. And it can be a planet, can do it also. So this is what we are looking for, asymmetrical, not blobs, but some global asymmetrical, like axisymmetric or messy nebula. If we are messy planetary nebulae, I think 15% of the non-spherical will be about messy, then maybe the companion of Lagvandra is a tertiary star. Maybe the other one already fell to the common envelope. So this is what we are looking for.
So the 30% that Death Star found, we should focus on those.
Why guest star?
The Death Star project found 30% of AGB stars being somewhat asymmetric.
Okay, yes. Yeah, okay. So if it's non-spherical, okay, yes.
It's the same percentage that found for his EV access.
This is an outcome of a merger of mass transfer. Yeah. I don't know how to make it otherwise, unless, if you have a dipole shape, this is a AGB moving through the interstellar medium, and you know that, Albert, you have several papers on Myra moving through the interstellar medium. So, yeah, but I'm talking about bipolar shape or point symmetric and so on.
Yeah. I'm going to raise, now we're going to go fairly fast to this discussion session, it's off fast, we go a little bit over time. So I had another question on Dimitri's talk about large grains. For one of the things we find in our post-AGB objects is disks that have a chemistry different from that of the central star. So we see oxygen-rich disks around carbon-rich stars. And those tend to be grains of indeed fairly large size. Millimeter size maybe up to. And they must have survived in that orbit, the circumbinary disk, for at least 100,000 years to give enough time to the star to have changed their chemistry. So in those models, do those dusty disks survive long enough? Can we really have grains over 100,000 years remain stable in orbits around these AGB stars?
I've I have a model for particulate discs in terms of the lifetime of particulate discs, depending on the geometry and the density, but it doesn't incorporate any chemistry, and I think that could be important. So it is possible to maintain a disk for that long, given its spatial distribution. But these particular disks, the exactly what you're talking about, I haven't modeled yet. Perhaps somebody else has.
Yeah, maybe someone in the audience has looked at the problem.
And it's a good project to pursue.
I think it's a very important one.
Yeah.
Something I hadn't thought about before your talk. But yeah, those long surviving disks during the AGB, are they a problem or an opportunity?
In one of the original papers, if you recall, Albert, there was a paper by Martin Cohen and one by Rens Vates, right, on this oxygen-rich disks around carbon-rich post-AGB stars. The Martin had suggested that this was the remnant from a previous phase of evolution to do with the planetary disk. So this was a long time ago now, 20 years ago. And so maybe, Dimitri, that's a kind of an interesting one, because if you can make the disk and then let it survive a violent phase of AGB pulses while the AGB starts turning carbon rich, but the disk needs to stay there in some fashion that's recognizable later on, then you got it.
No, that's a very good problem. That's right. Well, it's not a problem. I actually view it, as Albert said, more as an opportunity rather than a problem.
Pressure is on, Dimitri.
I'd like somebody to help me. please contact me.
Although the planetary disks, if that remains at this point, will not have anywhere near the mass compared to the dust in the stellar wind.
Yes, I think that's correct. Yes. I guess it depends on when you measure the mass in the stellar wind.
But I remember a very long time ago, people made the same suggestion about comets. During the AGB evolution, the comets will evaporate, and they are also a source of molecules and dust.
Actually, one of the oldest papers on white dwarf pollution is about exo Oort cloud comets, and it's from the late 80s. So yeah, there was work on this well before the field really took off. It's true. Right. And in general, there's more work on exocomets even around other types of stars now, because we actually do see these signatures in dippers and slightly evolved stars as well.
Okay, I've been given an absolute deadline of 10 minutes past 4 to end this discussion. So sorry for going in a bit over time on the discussion. I hope you don't mind. We'll have a break now because Zoom meetings need it. And we'll start again in 1 hour, not at 5 o'clock, so in 50 minutes.
Yeah, okay. I'll send you an email with the new link for the Zoom meeting. And well, we'll see again in 50 minutes.
Okay,
thank you, everybody.
Bye-bye.